Most engineering teams focus heavily on technical performance during product development. The product must meet requirements and perform reliably in the field. Many products that meet these objectives, however, can still be difficult and expensive to manufacture. Why is that? Well, this is related to manufacturing usually being treated as a downstream activity instead of a core engineering responsibility. In many organizations, manufacturing teams inherit designs that are already well defined, and at that point it becomes costly to make changes. The reality is that every engineering decision influences manufacturing, which is the foundation of design for manufacturing, also known as DFM. DFM is the practice of developing products that align engineering decisions with the capabilities and strengths of selected manufacturing processes. To produce parts effectively, engineers need to understand how products will be manufactured, make intentional decisions early in the development, and design around the strengths and limitations of the selected process. Manufacturing technologies continue to improve, and companies that recognize this fact can make better design decisions earlier, reducing production efficiencies before product launch, leading to lower total product cost. In this video, we're going to break down the principles behind DFM, how manufacturing process should influence engineering decisions, and practical methods used to improve manufacturability and produce lower costs before manufacturing begins. So what is the role of DFM during the concept design phase? In the concept design phase, a certain amount of abstraction and flexibility is required, and therefore DFM plays a smaller role. It's disruptive to add DFM in this part of the process because it'll obscure what you're trying to really achieve in terms of meeting requirements, establishing design intent, or evaluating the feasibility. That detail is going to drive you in a direction that's not going to really focus on the real intent during the concept phase, and therefore it's not advisable to add DFM very early in the concept phase. It's only once viable concepts emerge that DFM should influence the design. Early DFM will concentrate on process evaluation rather than detailed design features. Trade-off studies can be used to facilitate it. The goal is not a detailed design optimization, but rather to identify the most effective manufacturing processes. So in summary, DFM can be used during the concept phase, but the emphasis is directional rather than definitive, with a goal to find viable processes that can be used to manufacture parts. After completing the concept design phase, you're going to need to determine which manufacturing processes are going to be used for the parts that you've developed during the concept phase. You want to shift from can this work to what's the best way to produce it. You may have identified multiple manufacturing processes that are technically feasible, and you need to determine which process gives you the best trade-offs. Some of the trade-offs include castings versus machine components, forgings versus castings, weldings versus castings, or hydroforming versus metal stamping. There are many processes that could come up here. You may have 3 or 4 different processes for one part, and you need to determine which fits your particular part the best. You also want to avoid assuming that your in-house processes are the best processes for all the parts you have. Have a look at the vendors and see what processes they have available to them, and see whether any one of those processes is better suited to what you're trying to produce. And at that point, make a decision which way you want to go. Some of the considerations when evaluating which process to use are looking at the geometry, sizes, and tolerances, and determining whether any of these processes is unsuitable by just looking at those 3 items. Once you have eliminated some of the processes, then look at a final process selection by including product costs, production volume, production flexibility, the ability to meet requirements, repeatability, lead time, scalability, and you want to then down select to the concept that gives you the best trade-offs, and that way you have then a particular process that best works for that particular part. Next, we're going to cover methods, and these are techniques or best practices that have been developed over time by individuals who really understand the particular processes, but also understand the strengths of every process, and also know how to guide design professionals and how to best utilize those strengths and avoid the weaknesses for a particular process. These haven't been developed for every single process, but for those processes that have been developed, it's advisable to go and find those particular methods and understand how to utilize them and how to best use that in your design processes. For processes that don't have any methods developed, consult with your manufacturing team, try to understand what they know about utilizing the strengths of a particular process and which particular features to avoid and how best to utilize that within your design processes. We're going to cover a few examples here. The first example is that of a slot and tab construction that is used for sheet metal components. In this first example of a method, we're going to cover the slot and tab construction commonly used for sheet metal components. In this example, we have an orange sheet metal component and a green sheet metal component. Both of these have been laser cut. The orange one has then been bent with a press brake to get the two additional corners. And then once you have the slot and tab construction, you can now use these tabs and slots to locate the orange part onto the green part and assemble it fairly accurately, fast and consistently without any additional fixturing. This works because laser cutting is very accurate and very fast as well. It doesn't take much additional time to add the slots and the tabs during the laser cutting process, and thus it's very advantageous to do that during the cutting process than trying to do it later. It takes much longer to assemble the components, weld the components, than it takes to actually cut those components, and it's somewhat automated when it comes to the laser cutting process. There's not a operator actually cutting it. It's usually done with a program. The operator is usually a supervisor of the process rather than someone that's actually performing the process as such. So it's really quick and thus gives you an advantage during the assembly side of this. Another advantage is that when you have a part that's not accurately bent, now this is somewhat exaggerated, you can actually now bend the orange part into place if it's flexible enough, and then align the tab and slot to get an accurate corner, and then do the same for the second leg of this particular sheet metal component, and thus get a fairly accurate part without having to go back and rebend it or do anything special to the part. So it has multiple advantages. It's not useful for cutting processes such as flame cutting or plasma cutting, but very useful for laser cutting and potentially other cutting processes, but these processes need to be highly accurate in order to use this technique. For the second method, we're going to look at additive manufacturing. This method is particular to when 3D printing utilizes a layer type philosophy and then hardens the individual pieces that stay behind and form the actual part that you're going to have. For this particular example, I'm utilizing 145:1 gearbox that was printed with a 3D printer and then assembled with some metal components. As it turns out, this particular gearbox is the one on my bookshelf over here, and the gear that you see on your screen is the internal main wobble gear that wobbles from side to side to give you that 145:1 reduction. What's important here is that the teeth have to be fairly accurate in order to get the meshing action, but also in order to get where it's done repeatedly, it needs to be fairly strong as well. And thus it's important to orient these parts correctly within the machine in order to both get the meshing accuracy as well as the strength of the components. So in this particular case, it was important to orient the part horizontally in the machine such that the layer would coincide with this surface over here on the gear, and thus you get the best accuracy on this particular surface and also the best strength on the surface here. And so this is a technique that's used within 3D additive manufacturing. It's common to understand how the part is made in 3D printing. You can't just simply orient it in any direction. You really need to understand what has greater strength, what has greater accuracy, and so methods have been developed for 3D additive manufacturing as well, and this is an example of that. In this next example of a method, this is related to machining. The method is essentially looking at using chamfers rather than fillets, if at all possible. This generally reduces the machine time, and the reason for that is if you look at how parts are machined, this being the original shape here, if it's a fillet, then with one pass you could do a rough cut, get close to the final surface, and then do a final cut here in 2 passes. you would have the chamfer profile cut. Very often this is done in one pass because you can see it's just a flat run, and then it's just basically done in that one pass and gets you to the final shape fairly quickly. If you have a fillet and you use a flat tool, this is however not the case. You'll do your initial pass over here, and then you'd have to do another pass here, another pass here, yet another pass. Once you do all these passes, you still don't have the fillet shape. You still have a 3-cornered or 4-cornered part on each of these fillets. You'd have to do multiple more passes to get a more accurate rendition of the round feature here to get to that. This can be alleviated by using a round tool and thus get you to the final shape quicker than if you used a flat tool. But then you would need another tool for that, and that just takes additional resources and having to maintain that tool. So it's not always the case that it's going to take longer to produce a fillet, but for the most part it's going to take longer to produce fillets than chamfers. Now there's a reason why you want fillets. If you look at this corner over here, we have maintained the fillet in this corner here because that's a stress concentration, and you need to keep that fillet in order to reduce the amount of stresses. Otherwise, if you had a chamfer, you would have stress concentrations at each corner of that chamfer. So you can't use chamfers in every single case, but when you can use them, it's advisable to go ahead and use chamfers on machine components. Next, we're going to move away from just looking at the piece part and how it's designed for a particular process, or how to take advantage of the strengths of a particular process. There are broader implications to the business when you're designing a part. It's not just the part and the process it's made from, but there are other implications as well. We're going to have a look at those next, one of which is inventory. Every design decision has a direct impact on inventory. You need to reuse common components to try and reduce the amount of inventory that you have. You need to maximize the reuse of parts within your particular assembly, but also look at whether you can reuse parts or components from other assemblies that you produce. The more that you do this, the fewer unique parts you'll have in inventory, and therefore the fewer parts you need to manage, the fewer parts you need to purchase, and also the availability of these parts becomes easier to manage as these go into production or get sold to customers. You also want to go one step beyond that, and that's looking at the raw materials for a particular part or component. One example is sheet metal, where you have certain thicknesses and grades of material. You may be looking at a whole collection of sheet metal components that you actually build, and you may ideally want to be building those out of different materials and different thicknesses of material. But when you look at that, that is non-optimal. If you have, let's say, material grade of 50 KSI and you have one at 60 KSI, the difference between those two isn't that great, and you may be better just buying 60 KSI material and standardizing on 60 KSI material rather than buying the lower grade material. Looking at thicknesses when they're close together, try to standardize on certain thickness that covers more parts as such. When you do that, you can then use that one particular sheet for multiple components and just cut those once. You don't have to wait as long to be able to cut that whole sheet, because when you're laser cutting a particular sheet, you don't want to be just cutting one piece of the sheet. You want to be cutting the whole sheet rather than pieces. And then when you're done, all you have to do is collect all the components, and then you just have scrap and components that are useful. That's generally the most efficient way of processing it when it comes to sheet metal components. That reduces the handling, reduces the amount of pieces that you need to work with. And the more that you can do this, then the fewer particular elements or particular types of standard material that you have to store. The same as is true for components is also true for raw materials, that you want to minimize the number of raw materials that you want to be able to keep in your inventory, and thus streamline your sourcing organization, and thus they don't have to manage as many of these raw materials that they would otherwise have to look at. Another aspect that you want to look at is the quality. The number of errors that you have in your organization do cost money, and those can either cost money when you find those errors during manufacturing, or you can find those errors when your parts or components go to customers. It's more costly when those go to customers from a cost perspective, but also from a reputation perspective. You want to try and keep those to a minimum. There are design practices that help reduce assembly mistakes, fabrication errors, and you want to produce designs that minimize the ability to make mistakes when it comes to fabricating and assembling items. One philosophy that was developed by Toyota a number of years back is Poka Yoke. Poka Yoke is a Japanese term that directly translates into error proofing. You want to error proof assemblies where they can be assembled only one way, rather than being assembled multiple ways. If they're assembled multiple ways, one of those ways is most probably incorrect, and it's not going to give you the correct configuration and gives you a wrong assembly. And once you start welding on that assembly, then that part becomes unusable at that point. So you want to try to design your assemblies where there's only one correct way of assembling, and if you can't do that, at least have a method that picks up a warning or creates a warning to the operator that that part is not correctly assembled. It can be moved aside and it doesn't move any further. But ideally you want to try to get to the point where you can control it with something like a Poka Yoke method. Using design for manufacturing is challenging since it just keeps evolving. It's not static. Manufacturing methods, equipment, automation continue to change. Existing design practice may no longer represent the most effective approach, and you may need to revisit your engineering assumptions and determine whether they're still applicable. Improvements in tooling, automation, and software can significantly change the process capability and cost. And you also need to look at the methods that you use to adapt your designs to the processes. These will change as well as the processes, the actual manufacturing processes change too. The past trade-offs may no longer be valid, and you may look at new trade-offs or look at the trade-offs you had before and determine that they're no longer applicable. You may have immature processes that you considered immature in the past that are now viable processes that have matured in the time frame that you first looked at them and now need to be considered as well in your trade-offs. You need to look at those, include them, and determine whether they make sense. Those former cost penalties are no longer valid, and you may need to include the new processes. Examples include faster drilling methods where it's not as slow as it used to be and you try to do something different to drilling, or you have faster machining methods, you have lower cost additive manufacturing, or increased robotic automation during the manufacturing process. It's sometimes hard to do this all by yourself, so you need to include your manufacturing teams and suppliers and have a constant dialogue with them. Communicate with them, understand what the new processes are, what are the emerging technologies, what are the major cost drivers, what are the process limitations, and where is manufacturing going in the future. You need to include that in your decisions and maintain awareness of these changes so you can manage the processes to continually drive down your product cost. As we wrap up, it's important to remember that design for manufacturing is not a single tool, checklist, or review activity. It's a way of thinking that helps engineers align product designs with the realities of manufacturing. During the concept phase, DFM plays a supporting role. Its influence grows as teams start to identify manufacturing processes that offer the best balance of cost, quality, and performance. Process selection is an important decision made during development. Multiple manufacturing methods may be technically capable of producing a part, but some are better suited than others. The most effective solution comes from understanding trade-offs and selecting the process that provides the greatest overall value. Successful designs leverage the strengths of the chosen manufacturing process. Beyond manufacturing itself, DFM can create value throughout the business. Design decisions influence inventory levels, supply chain risk, lead times, and product quality. Well-executed DFM reduces waste, improves repeatability, and helps organizations operate more effectively. Finally, DFM needs to be constantly revisited. Manufacturing technologies, automation, software, and tooling continue to evolve, and organizations need to adapt. When applied consistently, DFM becomes a powerful tool for improving competitiveness, driving sustainable cost reduction. If you're interested in learning more about practical methods to reduce the cost of products, visit productcost.com. we provide training, tools, and resources focused on helping companies make better decisions and achieve measurable results.